Okay. Hi everyone, my name is Jolan Gauthier. I'm an engineer working at CEDRAT Technologies. It is a company that is based in Grenoble, in France, and we are mainly working on piezoelectric actuators. The outline of my presentation will be the following. So first I'll start with a little introduction to try to define what are smart materials. And since piezoelectricity is the core activity of my company, CEDRAT Technologies, I will have a second part, talking about the equations of the main equations of piezoelectricity theory, and then we will have a last part concerning applications and market of piezoelectric actuators. So first, what can be considered as a smart material? So there are several definitions in the literature as the smart materials are concerned. But what you can see here is that they are defined as materials that sense and react to environmental conditions or stimuli, and from various sources, meaning mechanical, chemical, electrical, also magnetic, thermal, etc. In the table that you have there, you can see the relations between several mediums, from electrical, magnetic, mechanical, thermal, and light. And for instance, in PulseCom project, we will use both these kind of smart materials, meaning first a conversion of light to strain using photostriction. I think you've seen the PMP material, photomobile polymer. And with this, we intend to use a PZL layer, so a piezoelectric layer, that will convert the mechanical stress into current. So this has potential for energy harvesting, for instance. Okay, so as I was mentioning, in PulseCom project we have the PMP. So you will find a lot of you had a lot of information about it during this short school. But if you want more information, you can see this publication that is available on the PulseCom project. So for these materials, the incident light is converted into mechanical strain. It is called photostriction. And with this, we intend to use the direct piezoelectric effect, meaning we will convert the mechanical stress induced by the mechanical strain of the PMP to electric current. So again, you can have more information on the website of PulseCom with this publication from UGA. So now we will go deeper into the piezoelectric equations and what defines piezoelectricity. And then we will finish by a little analysis before going to the main applications. So first, so piezoelectricity relates the mechanical strain and stresses into electricity. So first, what are mechanical strains? What are mechanical stresses? So the strain is the relative expansion of the materials in standard materials. We make the hypothesis of the small deformations in the elastic domain of the materials. So as you can see here in this little sample, the strain would be the variation of length divided by the initial length. So usually we talk about ppm for units because there are really small strains from -6 power. For piezoelectric materials, the typical strains are 0.1% or 1000 ppm. So it's a quantity that doesn't have a unit basically. But and then we can compute the stroke of the material by multiplying the length by the deformation. Then how to obtain the stresses? The stresses are the force per unit of surface. So it's actually the same units than a pressure, like Pascal or megapascals. So basically, if you have a surface which is equal to A and a force that is applied on this surface equal to F, you would have the stress, which is noted with the notation T, to be the force over the area. A positive stress would mean that the material is in expansion, and a negative stress would mean that the material is being contracted. So, piezoelectric effects. Piezoelectric effects relates to the conversion of electrical energy into mechanical energy, and reversely, we have also the conversion of mechanical energy to electrical energy. So we have the direct effect, which is used for sensing applications. So it's when you apply mechanical force, like you can see in the little picture here, you will have voltage. And on the opposite, the converse effect, if you apply voltage, you will have a deformation of the materials. So there is a lot of notations to explain the equations. So D is the piezoelectric coefficients, E is the electrical field, S would be the mechanical strain, D the electric displacement field, T the stresses, and P the polarization. So what is the polarizations? In the piezoelectric materials, we have the piezo ceramic that you can see here. We apply a really intense voltage in order to polarize the materials. And after, we can, once it's polarized, we can else use the converse piezoelectric effect or the direct piezoelectric effect to have the energy conversion between mechanical and electricity. There are amongst the piezoelectric materials, you have also some parasitic effects that are not often taken into account into the modelizations. But if we had to consider them, we have those two main parasitic effects. So the pyroelectric effect first, which relates the polarizations to the temperature of the material, and the electrorestrictive effect, electrorestriction, that relates the strain within the materials with the electric field. And the piezoelectric strain combines all of those effects. So you can sum the converse piezo effects, the electrorestriction, and the pyroelectric effect. And finally, the piezoelectric materials, which is often called PZT or PZL, or lead titanium zirconate, is a ferroelectric material. So we have to give this material remnant polarizations. And so, as I mentioned before, before the polarizations, the lattices into the materials are the local polarizations are like an isotropic in an isotropic configuration without a precise directions. And when we close the circuit, and we will polarize the materials with a high intensity voltage. And after, we will have a remaining, when we open again the circuit, we will have a remaining polarizations, a remnant polarizations, which is not the perfect polarization, but sufficient enough to have the piezoelectric effect. So during the polarizations, well, first, at the non-polarized state, as I mentioned, the lattices, the inner polarization of the lattices are like randomly chosen. But when we apply at the edges of the piezoelectric material a high voltage, they will be oriented in preferential directions. So this is step 2, up to, for instance, 150 volts. And then as long as we do not put a higher voltage than 150 volts, we can, for instance, reduce the voltage and then put voltage again, etc. And we have this hysteretic displacement with a residual displacement, which is linked to the polarized state. Okay, so let's go deeper into the piezoelectricity equations. So there are big equations, but we will simplify it afterwards. So first, we have to relate the mechanical strain with the mechanical stresses and the electrical field. So this is the direct piezo effect, and you have to relate then the electric displacement field with the stresses and the electric field. Okay, and this in every direction into space. And with these equations, we do not consider electrorestriction nor pyroelectric effects. So all the parasitic effects are removed. So it simplifies a bit the equations. If we have to put it on the matrix formulations, you can see here the strain, the electric charge displacement field, the stresses, and the electric fields that are linked to this bigger matrix using the mechanical compliance of the material and the piezoelectric coefficients. So you have three of them, three different, 1, 5, 3, 3, and 3, 1. I will explain after what it is. And also the permittivity coefficients that exist in ferroelectric materials. The three modes of deformations of piezoelectric material are the modes 3,3, 3,1, and 1,5. So for the mode 3,3, it's when the polarizations is aligned with the deformation of the ceramic, but also the electric field is aligned. So everything is in the same direction. It's the most common way for a piezoelectric crystal to be excited. Then you have, so it is called the longitudinal mode. Then you have the shear mode, when you induce shear strain in the materials. So it's when the deformations is perpendicular to the voltage, but aligned with the polarization. And finally, you have the third mode, which is the 3-1 mode, the transverse mode. It's when the voltage is aligned with the polarizations, but the mechanical forces or stresses are perpendicular. So you have these three modes of deformations. We will simplify the previous equations considering the longitudinal mode because it's the most simple to visualize. So it's when you have the electrical excitations, which is aligned with the polarizations, but also the deformation of the materials. So so in other directions, most of the component goes to 0, but we have to keep the mechanical strain because it's not 0 in the other direction because of the Poisson's ratio. And with what we have left, we can simplify the equations and have the mechanical strains up to several the perpendicular directions, the main directions, and the electric displacement field depending on the other constants that are the mechanical compliances, the piezoelectric coefficients, the mechanical stress, and the electrical field, and the permittivity for the displacement electric displacement field. So once we are there, we can write the electromechanical coupling effect, which is a formalism to estimate the efficiency of the energy conversion, the electromechanical energy conversions. So usually in an electromechanical device, you have the mutual electromechanical energy and the electrical energy and the mechanical energy. So this is a ratio that goes from 0 to 1, depending on the efficiency of your energy conversions. If you have a ratio of 1, it means you have a perfect energy conversions, which rarely exists in this world, but most likely you can have a conversion of 0.3 or 0.4 usually. So for each mode of deformations, you can write this coupling factor, and you can see that the electromechanical energy is the piezoelectric coefficient. So the and you can have here the electrical parts alone, so the permittivity, and the mechanical compliance part alone for the mechanical part. And as I said before, the perfect energy conversion would be that you have the coefficient of coupling would be equal to 1. But in the reality, there are a lot of losses in the piezoelectric materials. We mentioned the pyroelectric effects, but there is also the mechanical damping of your system. There are also coupling losses and dielectric losses, amongst other losses. This is to make a little synthesis. So you have to remember that you have 3 types of constants to characterize the piezo material. It's the mechanical compliance, the piezo coefficients, and the permittivity. And that you can link the mechanical strain to the mechanical stresses and the piezoelectric effects, which is induced by the electrical field, and the electrical induction, which is related to the stresses and the electrical field, by the piezo coefficients and the permittivity. We perform a little static analysis of an actuator, let's say. So you have this ceramic material, which is a piezoelectric material, and now we will use macro physical quantities because we had previously micro physical quantities, so deformation, etc. But it's kind of easier to talk about displacement, voltage, electric charge, etc., and forces. So, which is more common to mechanical and electricity parameters. So, if we do it, the previous equations can be written again and quite simplified, and we can plot the working curve of the piezo actuator. So you have here the force that is generated by your piezoelectric element. Here is the displacement, and it is linked to the mechanical stiffness, which is here. Okay. When you have no displacement, so your piezo ceramic is totally blocked, it generates the maximum force onto your system. But on the opposite, if you have a force which is if you have a free displacement, so the force is equal to 0, you would have the highest displacement possible. This is what I try to explain here. Also, we have seen that if we take a piezo ceramic that is polarized to 150 volts, you would have the better performances. But you could also work with this piezo ceramic at lower voltages, for instance, 50 volts. But you would have lower forces and lower stroke. So it's possible, but it's a bit less efficient usually into the piezoelectric actuators. So this was the characteristic curves of the piezoelectric. But in the real world, it's not totally linear. I've shown here linear curves, but it's not in the real world. It's not like that because you have the parasitic effects I mentioned before, so pyroelectric effect, electrorestriction, etc., which makes that you don't have a linear relation between the voltage that you apply at the edge of your piezo ceramics and the displacement or the deformation of the ceramic. You have indeed that kind of curve in red, which is called the hysteretic curve of the piezo materials. So you can have differences up to 10 to 15% between the linear model, which is used for the modelizations, and the reality here. Let's have a little example of actuators. I will show you the impact on the hysteretic curve in case you have a stiffness acting against the actuator. Well, most likely the actuator is acting against the spring, and when your actuator is trying to move a mass. In such a case, when your actuator is acting against a spring, so you will have the blue curve. You will have less displacement because you add the stiffness of the spring, which reduces the total stroke that you can reach with your actuator. In the opposite, if you have only a mass at the edge of your actuator, you would have a little deformations due to gravity. Well, we suppose here that the mass is aligned with the I mean the piezo actuator is aligned with the gravity. So that means you have a little preload that would modify the displacement at the displacement at 0 volts. But then you would have the same shape than the red curve at free displacement, because you have only the gravity that is acting on your mass. A little recap here. You have a so I mentioned before this one, but we have added 3 new type of integrated constants to characterize this time piezo actuators: the stiffness K, the coupling N, and the capacitance T. To link the voltage that you apply at the edge of your piezo ceramic, the displacements of your actuator, and the force that is exerted at the edge of your piezo ceramic. And about the electrical, for the electrical, you have the electrical charge here. And do not mix the big K, which is the stiffness, mechanical stiffness, and the lower K, which is the coupling coefficient we've seen before. Now, what happens when we try to put when we are in the dynamic regime of our piezo actuators? So these previous equations that are if you remember well, are the characteristic curve of our actuator can be derivated, and by introducing the pulsation, so the time, and we can now link the force to the voltage and the speed, and the current with the voltage and the speed, if we derive the equations. This means that we can write it with an equivalent electromechanical circuits notation. Here you have the electrical branch and the motional branch, which are linked by the force factor coefficient here, which is kind of your transformer. So it converts electrical energy into motional energy. We can also add the losses, so the dielectric losses, and the mechanical damping friction, which is the friction. Then we can also add the boundary conditions of your piezoelectric actuators. So in case of a free configurations, your piezoelectric actuator would be would have a stroke divided by 2 if you look at the center of your actuator, but you would have a higher resonant frequency. In case of a blockade free configuration, which is the most used configuration, you would block the back side of the actuator, which means that all the displacements would be on the right side of your actuator, but you would have a lower frequency than the free configuration. And in the end, if you try the block configurations, which means both edges cannot are rigidly fixed, then you have only a force when your actuator only generates force when you apply voltage in it. If we try to add to clamp the actuator from one side, and we add the mass at the other side, you have here the modification of the electromechanical circuits, which is just that you have been adding here something that stores the energy, in which case, in this case, a moving mass. So from the electrical point of view, it acts like an inductance. Then you can try to write the displacement of this transfer function, which links the displacement of the mass over the voltage. So the displacement of your piezo actuators divided by the voltage you supply to it. If you do this, you will have 2 main parameters that will describe the behavior of your actuator. You will have the mechanical resonance pulsation, omega R, and the mechanical quality factor, Q. If we simplify these transfer functions using these 2 parameters, you can write it, it's right down here, and you can plot it here. And what can be seen on this transfer function? It means that at low frequencies, low pulsations, you would have a constant stroke depending on the voltage. So if you apply for a fixed voltage that will give you a displacement, and which would be equal to the numerator of the main transfer function. At the resonance, you will have the quality factor times, the stroke would be the quality factor times the static stroke at the resonance. And after the resonance, you would have you would act as a force generator, but no more displacement generation. And the effects on the piezo actuators are the following: is that if you have a high resonance frequency and a low quality factor, especially a low quality factor means that the system is correctly damped, so you have less oscillations that with a high quality factor. And having high resonance frequency means that you have a higher range of frequency to work with static applications. This is resumed on the following table. So if you, with your actuator, you try to work in the lowest regions of frequency, you would generate displacement. And this is very practical for positioning systems, injection wells, and also shutters for optical applications. If you try to work at the resonance of your actuator, you will generate vibrations. And this is very useful for sonic and ultrasonic transducers, but also acoustic generators. And if you work above the resonance frequency, you will work you will generate a dynamic force. And this is very useful for proof mass dampers, for instance. And now we can summarize with a few more additions here what I've said. The electromechanical analogy is very useful to make dynamic modelings, so for harmonic but also transient states of your actuator. And during the test, what we use to have the transfer function that I've shown before are usually impedance meter, but not only, we can use also lasers to link with the displacement. But this electromechanical analogy is used for design for three-dimension piezo actuators, but we often use also finite elements methods because this doesn't give you much information about the stresses. This approximation, and also this is only representing one mode of excitation. You have only one peak here. While in reality, you would have other peaks after. But this is, since the amplitude is really low, it can often be simplified. Not every time, but often be simplified. And this is also very interesting for designing electronics that will drive the actuators, because it can simulate the equivalent electrical load that will be seen by the electronics. And now we can finish with some applications of what I've been presenting you. So you have, I will be presenting these few applications for position control, optical control, fluid control, vibration control, energy harvesting, and a bit of sensor using the direct piezo effect. But first, I'd like to remind you what's the technology readiness level. So this is a scale that goes from 1 to 9, which defines how advanced and how characterized is your actuator. So, for instance, for PulseCom projects, we are between TRL1 to TRL3, because what we want to reach in PulseCom is an experimental proof of concepts. Then, with more time and more efforts, we will be perhaps able to validate the technology in laboratory and up to relevant environments. So, and afterwards, there is the last phase of deployment, which consists in demonstrate that the prototype works in operational environments, to qualify the system, and then to bring it to the market and generalize its use on the market. So for position control, I've chosen to present you this actuator, this piezoelectric actuators. So you have here 8 piezo actuators here, which is from APA for amplified piezo actuators, and 1 PPA, which are CTEC standard actuator, which is used as a parallel pre-stressed actuator. So you have here a 3-axis stage. So with all those APAs, you can move in the X directions. This one allows to move in the perpendicular directions. And the last one, the PPA, is used to move in the vertical directions. So this system was embedded onto the Rosetta satellite that that was launched in 2004 and has reached a comet between Earth and the Mars planet in 2016. The main advantages of why did we need such actuator? It was to analyze the dust onto the comet. For the MIDES IFM instruments, I've put you some reference here if you want to check on the internet. This stage was featuring displacement onto 2 axes, 100 micrometers and 8 micrometers, 100 micrometers and 8 micrometers vertically, and had a resolution of 4 nanometers. So it's a very precise positioning. And you have to know that in piezoelectric actuators, the theoretical resolution is infinitesimal, infinitely low, but you are always limited by the electrical noise because it converts electrical energy to mechanical energy. So the 4 nanometers resolutions is a consequence of having electrical noises into the electrons. You have here another versions of such position control stage, so only 2 axes this time. And what's is interesting is that it's mechanically, electrically, and centered and thermally compensated using strain gauges, which is something we can put onto the piezo ceramic to perform closed loop control and thus compensate the thermal modifications of the environments on the central part, which is moving. Another kind of applications would be optical control. For instance, using the same actuator than I've shown here, you can perform the oversampling technique by merging 4 successive pictures that you would take while the XY stage moves the lens here. So you can take several pictures at several key points. In this case, the maximum corresponds to the 0.5 pixels of the sensor. And with this, you can have better picture qualities by merging 4 images at each time for each picture. So you can see the comparisons. On the left, it is without the oversampling technique. So you have a lot of blurred areas on the pictures. And on the right, it's with the you have a better quality of the picture using this oversampling technique. So this is obtained by using piezoelectric actuator. The third kind of applications are for fluid control, especially for proportional piezo wells. Here you have a piezoelectric actuator. You can see it on the picture. This can allow to open and close a nozzle here. So this is a kind of a piezo well. In PulseCom project, we will try also to make an Opto well this time, so working with light excitations. And by using the strain gauges, we could close the loop of the piezo valve and have a linearizations of the flow that is of the liquid flow that is flowing depending on the voltage we apply on the piezo actuator. Another kind of piezo actuator would be the hydrostatic actuators. As you can see here, you have a little piezo well on this test bench. The input of the fluid goes there, and the output would be here, and here. And the well has shown no leakage up to 220 bars in close position of the piezo actuators that you have here. And for as proportional pneumatic valves are concerned, we have manufactured with an APA from CTech, a valve that was able again to close a fluid circuit, close and open a fluid circuit. Another very interesting applications for piezoelectric actuator, which has a kind of a market, I think, is for the vibration control applications. So during the machining, you have the tool that you have here is machining the material here. For instance, it is a turning application. And during machining, you have a lot of vibrations onto the part, and sometimes you can have a very bad state surface at the end of the machining. So to counter the vibrations, here it is used a piezo actuator here in green, which generated forces according to the vibrations that was exerted on the tool by the parts to be manufactured. The loop was indeed closed with the force sensor that you have here, so that you can see that the actuator was acting as a force to counteract the force of the vibrations, but only along one direction. So this is the results when you have no active damping. So when the actuator is not supplying with voltage and the control loop is not closed, and when you activate the closed loop, so you supply the actuator with voltage depending on the vibration that is exerted at the level of the tool. You have far lower accelerations at the level of the tool and the parts, so less, which means you have less vibrations and better quality, surface quality. I think I will be quick on this one because my colleague Mashik has already spoken about energy harvesting with smart actuators. But we also made several piezo actuators with big masses and adapted the impedance. So it means the serial resistance with the piezo actuator in order to maximize the energy harvesting of the actuator. And lastly, we have the sensing applications, so which this time use the direct piezoelectric effects. You can perform some force sensor, pressure sensors, strain sensors, and also accelerometers. You have a cut view here. And using the electroacoustic effects of the piezoelectric material, you can also make sonar piezoelectric transducers, ultrasonic transducer. And finally, with this parasitic effect, which is the pyroelectric effect, you can make temperature sensors out of piezoelectric materials. This is the end of my presentation. I don't know if you have any question, but feel free to send it if it's the case.